Thermal expansion. Nearly all materials expand when their temperature is raised and contract when their temperature is lowered. For example, high temperatures make the liquid expand in a mercury thermometer and bend by metallic strips. Furthermore, you can also loosen up a metal jar lid when running over hot water. So these are all examples of thermal expansion. And for thermal expansion, we have three types. And these expansion are classified according to what dimensions are affected. So first is the linear expansion. It is a change in any one dimension of a solid. Here, we use a coefficient of linear expansion, which is denoted as alpha, to signify the change in length per degree change in temperature. So this constant has different values for different materials. So when we say linear, alam naman natin that linear is a line. So ibig sabihin, one dimension lang ng isang solid or isang object yung naaapektuhan. So to determine the extent of an object's linear expansion, so we use this formula below. So delta L is equals to alpha multiplied by L sub L naught or L sub 0 multiplied by delta T. So delta L is your length change. So let us write here. So delta L is your length change. Since we know that delta is equals to the represents change. So alpha again is your coefficient of linear expansion. So CoFLE. And L sub 0 is your initial length. So initial length, initial width, or initial thickness. Ayan. So dito papasok yan. And the delta T represents your temperature change. Ayan. So here, so these are the variables that we must take into consideration when we want to determine the extent of linear expansion in an object. So for many materials, every linear dimension changes. Therefore, your initial length or the variable L could mean either thickness, either length, or diameter of a hole. If thermal expansion occurs in two dimensions, then it is called area expansion. The same process is followed, kagaya nung kanina sa linear expansion, but this time, we will now use the coefficient of area expansion, which is denoted by the Greek letter gamma, to denote the change in area per unit initial area per degree change in temperature. So, it is approximately twice the coefficient of the linear expansion. So, to determine the extent of an object's area expansion, so we use this formula below. So, this formula is just like the previous, but with some variables change. So, instead of L, we now use the variable A, which means the change in area and your initial area, respectively. And instead of alpha, we now use gamma, which is your coefficient of area expansion. Increasing temperatures usually causes increases in volume for both solids and liquids. So just as with linear and area expansion, experiments show that if the temperature change or delta T is less than 100 degrees Celsius or so, the increase in volume or delta V is approximately proportional to both the temperature change and the initial volume V sub 0, which is represented by our formula here. So just like the previous expansion formulas, same format but different variables. Here, our V represents volume, and instead of alpha or gamma, we use the coefficient of volume expansion, which is beta, and it is approximately thrice the coefficient of the linear expansion.
An aluminum alloy rod has a length of 10 centimeters at 20 degrees Celsius and a length of 10.015 centimeters at the boiling point of water. What is the length of the rod at the freezing point of water? What is the temperature if the length of the rod is 10.009 centimeters? So for this formula, we are given the final length and initial length of the aluminum alloy. And we will find first the coefficient of linear expansion. So we have the formula here, delta L equals alpha LO delta T. So we need to find what is alpha. So we derive that is equal to alpha equals delta L over LO delta T. So recall that delta T is the change in temperature and delta L is the change in length. So for the change of length, we have the final length that is equal to 10.015 centimeters minus the initial length that is equal to 10 centimeters over the initial length that is equal to 10 centimeters multiplied by 80 degrees Celsius, because it is mentioned that the boiling point of water is 100 degrees Celsius and we have an initial temperature of 20 degrees Celsius. So alpha is equal to 1.875 times 10 raised to negative 5 per degree Celsius. So for the next problem, we are asked to find what is the final length at the freezing point of water. So we have L equals LO plus alpha LO delta T. So the initial length is equal to 10 centimeters plus alpha 1.875 times 10 raised to negative 5 per degree Celsius, while the LO is just equal to 10 centimeters, while the change in temperature, recall that the freezing point of water is 0 degrees Celsius minus the initial temperature of 20 degrees Celsius, and if you calculate, that is equal to 9.996 centimeters. Finally, we are asked to find the final temperature if it is equal to 10.009 centimeters. So we are using the same formula, but in this case, we are finding the final temperature as we have given the final length. So that is equal to 10.009 minus 10 centimeters equals 1.875 times 10 raised to negative 5 per degree Celsius multiplied by the initial length that is equal to 10 centimeters multiplied by the change in temperature that is equal to T minus 20 degrees Celsius. Solving for the final temperature T will give you 68 degrees Celsius. A steel rod is 3 centimeters in diameter at 25 degrees Celsius. A brass ring has an interior diameter of 2.992 centimeters at 25 degrees Celsius. At what common temperature will the ring just slide onto the rod? So for this problem, we will use linear expansion, and in this case, you will use the diameter as the length. So we will equate the linear expansion equations for steel and brass separately, and we just equate them in order to get the common temperature the problem is asking for. So we have DSO plus alpha DSO delta T equals DBO plus alpha B DBO delta T, where DSO is the diameter of steel and AS or alpha S is the linear coefficient of expansion, while DBO is the initial diameter of brass and alpha B is the coefficient of linear expansion of brass, while delta T is the change in temperature. But we are looking for the common temperature, so let us assume that the initial temperature for both cases is already given, which is 25 degrees Celsius. What we are looking for is the final temperature. So by deriving the equation, we get DSO minus DBO over alpha B DBO minus alpha S DSO. And we substitute for the initial diameter of steel, we have 3 centimeters. For the initial diameter of brass, we have 2.992 centimeters. So in the table of coefficient of linear expansion, we have for brass, we have 18 times 10 raised to negative 6 per degree Celsius, while alpha S or alpha in steel is equal to 12 times 10 raised to negative 6 per degree Celsius. So by equating them in the equation, we have delta T equals 448 degrees Celsius. So since we are looking for the final temperature, you equate delta T equals final minus initial temperature. And to find for the final temperature, you add the initial temperature and the change in temperature. That is 448 plus 25 degrees Celsius equals 473 degrees Celsius.
Thank you for listening. I hope you learned something today and see you on the next discussion video.